Hello, I am Jules Vidal. I'm a PhD student at Sorbonne University in Paris. I will present our work on the approximation of persistence diagrams with guarantee. So the persistence diagram is a tool from topological data analysis. Topological data analysis forms a collection of techniques that enable the efficient and generic extraction of features in the data. This diagram describes the repartition of topological features of the data that are associated with the critical points of a scalar field. And the relative importance of features is characterized by their topological persistence. Large bars in a diagram correspond to high persistence features that describe the main structures of the data, while small bars near the diagonal are associated with small features that are likely to be noise. So the persistence diagrams visually convey the number and salience of features in the data and enable an efficient and robust data reduction. So it's a great tool for the visual exploration of features of the data. However, the computation of the persistence diagram can take some time on large and noisy datasets. For instance, this diagram on the backpack dataset takes 70 seconds to compute on my machine with the topology toolkit. So it's not unreasonable, but it can still limit the interactivity of the analysis. And so this motivates the development of approximation techniques in order to reduce computation times and increase interactivity. So in general, a fully exact result is not really needed in the applications, as the major part of the output diagram usually correspond to small persistence pairs. For instance, in the previous example, the diagram has around 2 million pairs, and here is the diagram constituted of the 20,000 highest persistence pairs. So these are the remaining pairs, and so we'll see that a full precision on these pairs may not be really needed, as they describe small features which are likely to be noise. In the applications, it's very common to threshold the diagram to only keep the highest pairs anyway. Another point is that we would want to provide theoretical guarantees on our results. So in this work, we focus on providing guarantees on the bottleneck distance between our approximation and the exact diagram. The bottleneck distance is a well-established metric on the space of persistence diagrams, with nice stability properties. In particular, the distance between the diagrams of two scalar fields is bounded by the uniform distance between these fields. And so we use this stability property to introduce an approximation method for persistence diagrams with user-controlled guarantees on the bottleneck distance to the exact result. We also document a strategy to visually encode the uncertainty related to our visualizations. And additionally, we provide a reference implementation for replicability purposes. So let's start with a naive baseline approach to the problem. Here is our input scalar field f. And given the stability bound that we've mentioned previously, it's fairly easy to build an approximation of a persistence diagram with guarantees on the bottleneck error. For instance, we just need to compute a staircase function, f staircase, that approximates f with a certain step of height to epsilon. And in that case, the uniform distance between the fields is bounded by epsilon, and as such, so is the bottleneck distance between their persistence diagrams. However, when we look at the persistence diagrams, we see that the diagram approximation is not very useful, as lots of the critical points are colocalized in the birth-death space. And this diagram may be close to the exact one in terms of bottleneck distance. It does not visually resemble the exact result. So our strategy to address this issue is to use a multi-resolution approach to finally approximate f. And the goal is to build an approximation, let's call it f hat, which is more accurate than the field f staircase, and that still provides the same guarantees. And additionally, we would like the computation to be faster when the tolerance on the bottleneck error is loose. And to achieve this, we base our approach on a previous work that was published in IEEE TVCG this year, that I will actually present later this week. So in this work, we introduced a progressive approach to the computation of topological representation of scalar fields. And we used a progressive hierarchical representation of the input data that enable efficient updates of topological representation between resolution levels. And to briefly get into the details, we can identify vertices that break the monotony of edges as they are inserted in the hierarchy. For instance, if we look at this edge, this is the vertex with the higher scalar value, and this is the lower vertex. And as this vertex is inserted at the middle, it becomes the highest vertex. So this breaks the overall monotony of the edge, right? We call this vertex a non-monotonic vertex. And in contrast, this vertex has a scalar value that is in between the values of these two vertices, and as such, the monotony of this edge is preserved. And we can show that if a new vertex is monotonic, and that all his new neighbors are monotonic as well, it is at a regular point of the field. This allows us to detect with very little computation a large part of the regular vertices in the field. And we say that these vertices are topologically invariant. This greatly speeds up the computation of the critical points of the field. And from the critical points, we can deduce the persistence diagram. We launch integral lines from the saddle points towards the extrema, and then we post-process all the merge events between connected components of sublevel sets that were listed that way. And as a result, the method that we will present here consists in artificially increasing the number of topologically invariant vertices, thus effectively increasing the speed of the approach. And we will locally modify the scalar field in an effort to reduce the number of non-monotonic vertices through a process that we call vertex folding. So here is an update between two resolution levels, and this is a 3D view of the scalar field. If we look at this vertex, we see that it breaks the monotony of this edge upon its insertion. So it's a non-monotonic vertex, and thus it reduces the number of topologically invariant vertices in the hierarchy. As it happens, the insertion of this vertex creates a saddle point here and a maximum there. So we noticed that we can artificially change the scalar value of this vertex as it is inserted in order to guarantee its monotony. So we set the new value to be the linear interpolation of the values of the vertices previously forming the edge. So this process that we call folding ensures the monotony of the vertex. And in fact, here it is now a topologically invariant vertex that we know to be regular. So the strategy for the computation of f hat is thus the following. Given a target bound on the bottleneck error epsilon, we process the whole hierarchy and we fold every non-monotonic vertex if the displacement value delta is lower than epsilon. And here is the exact hierarchy, and here is our approximation. So for instance, this vertex is non-monotonic, so its displacement value delta is lower than epsilon, which means it gets folded as it is inserted. Then the scalar value doesn't evolve anymore. By construction, the uniform distance between our approximate function f hat and the exact field f is bounded by epsilon. Folding a large part of the non-monotonic vertices increases the number of topologically invariant vertices, and this allows us to efficiently compute the critical points from which we can deduce the persistence diagram, as explained previously. Here is the final approximated persistence diagram, and we can observe that it visually resembles the diagram of the exact field minus the small persistence pairs. And of course, the bottleneck distance between the two diagrams is guaranteed to be bounded by epsilon. In the remainder, we refer to epsilon as a percentage of the whole function range. And that's because this range corresponds to the worst bottleneck error possible. As such, an epsilon of 0% corresponds to the exact computation, while epsilon equal 30% correspond to an approximation with the tolerance of 30% on the relative bottleneck error. We can visually convey the uncertainty related to our approximation directly in the persistence diagrams. For this, we use a red band of height 2 epsilon near the diagonal to indicate an uncertain zone where the persistence pairs may not exist in the exact diagram, like the small white pair. And in contrast, all the pairs that are above this band are guaranteed to exist in the exact diagram. And their correct location is bounded by a square of side 2 epsilon. So the exact pairs, here shown in transparent, are guaranteed to be in these squares. And we carried out a series of experiments and started to compare our method to the naive staircase approach. And note that both approaches provide the same guarantees on the bottleneck error. We found that our approximate persistence diagrams are closer visually to the exact result than the diagram of the staircase function. Our critical points are also better capture the features of the original data. So globally, our approximation is more accurate, both in regard to the approximated scalar field and the corresponding diagram. This is confirmed quantitatively, as we showed that on our datasets, our approximated diagrams are 5 times more accurate on average, in terms of the Wasserstein distance to the exact result. And our approximated fields are 2 times more accurate in terms of the L2 distance. Performance-wise, we found that our approach indeed enables to reduce the runtime, and we compared to reference implementations and observed a decrease of 18% of the computation time on average for a mild relative bottleneck error of 5%. Globally, our method works based on noisy datasets, for which we observed up to a reduction of 48% of the runtime. It's related to a high increase in the number of topologically invariant vertices. So for smoother datasets that already exhibit a large number of topologically invariant vertices, the speedup is reduced. Here is an example of our approximations used to visualize relevant features in the data. On the foot dataset, our diagram correctly captured the high persistence maxima of the field that correspond to the bones of the toes. The approximated field resulting from vertex folding is more precise in the vicinity of high persistence features. For instance, the bones are well captured, and in contrast, more vertices are folded in the regions of low persistence features, so typically the skin of the foot. The same phenomenon can be seen on the backpack dataset, where the high density objects inside the bag are well preserved, which is seen in the volume rendering here, and while ISO contours that capture the cloth of the bag illustrate that the field in this region is degraded. This observation suggests that our method provides a better approximation of high persistence features and a degraded evaluation for less persistence features. And this, I recall, was one of the motivations for our work. So this point is confirmed when looking at the number of persistence pairs in the approximate diagrams, and specifically the number of noisy pairs in the uncertain zone below the red band is significantly lower than the amount in the exact diagram. And this amount is shown between parentheses. On the contrary, the number of high persistence features is pretty much the same. And so the real difference between the exact diagrams and our approximations lie in the small noisy pairs. Here we illustrate that we can visually convey indications about the approximation uncertainty. Once again, the pairs that are guaranteed to be in exact diagrams are shown with a square that bound their correct location. A red band indicates the pair that may not really be in a part of the exact result. So between this approximation at 10% error and this one at 5%, we have confirmed that this medium persistence pair here actually corresponds to a real feature in the data. So this work addresses a limitation of the previous work that I mentioned that was published to IEEE TVCG. And basically we already could compute approximations of persistence diagrams by interrupting a progressive computation. And this usually results in good approximations in practice, but it can happen that high persistence features are not captured until the very end of the computation. So this can happen when we have sharp spikes in the data, for instance. And this is shown in this example, where the best approximation provided by the interruption of the progressive approach actually results in a diagram that is quite far from the exact result. And in contrast with our approximation, since we have guarantees on the result, high persistence features are correctly captured. In conclusion, we presented a new method for the approximate computation of persistence diagrams. Our method improves the interactivity of the computation as it reduces computation times, and it provides guarantees on the diagram approximations. And we showed that it's more accurate than a simple baseline staircase approach, and that it focuses the computation load on high persistence features of the data. And in the future, we would like to find ways to resume the computation where the accuracy of an approximation needs to be increased without recomputing it from scratch. Moreover, it could be interesting to try and provide guarantees in terms of the Wasserstein distance, which is more useful in practice than the simple bottleneck distance. And finally, all this work will soon be integrated in the topology toolkit, so you will be able to compute approximations of persistence diagrams in TTK very soon. So stay tuned for that. And thank you very much for your attention. I will be happy to answer questions now.